This is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. Hi, Efren. It's awesome to see you. Good afternoon indeed. Go ahead, tell me on the whiteboard, who is your biggest supporter and why? So go ahead, type on the whiteboard your biggest supporter and why. Want to know? Go ahead, get your answers up there. Hi, Chanel. Hi, Taylor. Good to see all of you. Go ahead, open up your ticket once you see those links in the chat box. Password is underneath the links as well. Go ahead, type on the board your biggest supporter and why. Go ahead, get your answers up there. Awesome. I see Efren beginning to work on the board. Let's get lots of participation. It's already noon. We should be wide awake and ready to go. Hi, Blossom. Hi, Isaiah. Good to see you. Awesome. All right, Efren's got his answer up on the board. Everyone else, let's participate. I want to hear from Amanda and Ashton and Chanel and Damien and Dorian. Get your answers up on the whiteboard. Same with you, Isaiah, Elias, Ethan. Go ahead, tell me who is your biggest supporter and why. Would love to hear from Jacob and Kyler. Letty, go ahead, get your answers on the board. Awesome, good to see you, Rosie. Welcome to class. Hi, Noah. Go ahead, open up your ticket, and then let me know who is your biggest supporter and why. Get your answers up on the board. Looking good. Yolese, Tristan. Answers on the board, please. Taylor, Shoshana, Rosie, Blossom, Parker, Orlando. Let's hear from everybody up on the board. Hi, Bree. Good to see you. Go ahead and tell me who is your biggest supporter and why. Awesome. I got an answer from Amanda and Letty. Excellent. Thank you. I see Taylor on the board. Love it. Lots of good answers up there. Dorian is on the board. Give you another 45 seconds, everyone. Get your answers up there, and then we're going to go ahead and get started. All right. You can keep on typing up there. You can finish your typing or start typing, but we are going to go ahead and start going over these together. So let's see here. Yes, I helped Efren this morning during support session working on the 2B lab, so I'm glad I was able to support you in that way. Let's see here, Dorian, you said, kind of hard, you don't have just one supporter, of course, right? So you have many supporters, family, friends, and teachers. I am so happy that you consider all of them to be supporting you. Let's see, Amanda, you said your mom, she's done and went, I think that you meant to say everywhere, that you want to or something. Oh no, Efren. Yeah, parents can definitely be a great support, exactly. Let's see here, Taylor, you said your parents are supporting you wanting to be a flight attendant. Flight attendant, that's a super cool job. You get to travel all over the place. Kind of weird hours though, I would have to say. And it's really cool once you get more experience because then you can choose a lot of the different places you want to go to. You get more preference, which is great. I have an uncle who's a flight attendant, has been a flight attendant for like 40 years, and it was a pretty good gig for him. Letty, you said your sister because she's always been there for you. Yeah, it was very cool. And Caleb, you said your grandmother. Awesome. All right. So what I just want to tell you guys is remember yesterday at the start of class, we discussed some obstacles that we sometimes have to meeting our goals. And sometimes those obstacles can actually be other people influencing us, right? So a way that we can begin to overcome that kind of obstacle is by thinking about who can really support us. And so what I want you to do is I want you to be communicating with them about your goals and asking them to check in on you on whether or not you're meeting your goals, right? So be like, hey, parents, make sure I'm waking up on time, or parents, encourage me to go to the gym, or encourage me to check my grades every day, and just kind of keep that dialogue open and make sure that you have your biggest supporters actually knowing how to support you best. Smiley faces if that makes sense. Sometimes people want to support you, but they just don't know how to. So you have to communicate with them. How can they best support you? Awesome. Thank you. I'm getting those smiley faces. Love it. All right, let's go ahead and get started today. Please open up your attendance ticket. The links are in the chat box. Password is right beneath the links as well. Go ahead, give me a green check if you have been able to get that open, as long as you're not having issues. Awesome. Hi, Josiah. Hi, Jody. Good to see you. Looking good. All right, I do see a lot of green checks, so it looks like we're not having any issues opening that up today. That's awesome. We are officially on day 8 out of 45 for quarter number 4. Today we are going to be finishing up our content for Unit 2. We're going to be talking about thermodynamics. So that's what we're going to take a look at, and tomorrow we do have a game day, and if you come to class and participate tomorrow, you can get your 10 points through the game day. Otherwise, you will have to do an alternative assignment, which is just not as fun. All right, so that's what's happening tomorrow. I know, it feels like a lot, right? After you're like, it's only been 8 days, what? All right, go ahead. So today we're going to be talking about states of matter, right? We've been talking about that, right? We've talked about phase changes. Today we're going to take a little bit more of a look at this idea of heat and energy, specifically the study of heat and energy, which is called thermodynamics. So that's where we're kind of going today. So we're going to talk about the 3 laws of thermodynamics. For some reason in physical science, there seems to be a lot of times where laws come in 3s. So 3 laws of thermodynamics. We're going to talk about what thermal energy is and how those are related to phase changes. And then we're going to determine how energy is able to actually cause a phase change. Okay? And it's a pretty short quiz today at the end of class, so we will knock that out of the park. So here's our mind map talking about matter, how it can change, how it can move, how it's composed. So that's what we're talking about. So thermodynamics. Now, how many of you have ever heard the term thermo before? Think about like thermal underwear. What do you think of when you hear the word thermal? Go ahead, tell me in the chat box. What do you think of when you hear the word thermal? Kind of like thermal underwear. What's the purpose of thermal underwear? Yes. Yeah, exactly. You should be thinking thermo, the prefix thermo means warm, right? Or in this case, we're talking about heat. And dynamics, okay, do you think a person who is dynamic, like a dynamic speaker, do you think there's someone that like stands really still or someone that like moves around the stage, uses their arms, interacts with the crowd? What do you think of dynamics, right? When you say dynamic. Yeah, you should think of move, right? So dynamics means this idea of movement. So thermodynamics is a science. The science of thermodynamics is the study of how heat energy moves. Smiley faces if that makes sense, how we kind of broke down that word and we're able to understand what that word means, how heat energy moves. Awesome. Thank you, Efren. Thank you, Orlando. Good. Now, there are 3 main laws of thermodynamics. The first law is related to just energy in general. The second law is related to what's called entropy. How many of you have ever heard the term entropy before? We're going to talk a little bit about what that really means today. And then the third law is related to temperature. So we're going to talk a little bit today about what absolute zero is. Again, terms you might have heard at times in your life, but you might not exactly know what they mean. So today we're going to learn something, right? So the first law of thermodynamics, you already know the first law of thermodynamics. We've talked about it a bajillion times. It is called the conservation of energy. And do you guys remember what's another word for to conserve, right? Think about it, starts with an S. What is another word for conserving energy? Go ahead, tell me in the chat box. What's another way you could say conserve? Yeah, we could say saving, exactly. So conservation, you should think of this idea of saving energy, right? So energy, okay, can change. Of course it can change. That happens all the time. How many of you, for example, today, tell me what did you eat for breakfast? Go ahead, tell me what you had for breakfast. So example, let's see here. What did I have for breakfast today? I had some oatmeal. I had a banana and strawberry smoothie. Yeah, a protein chocolate bar, French toast, delicious. I haven't had French toast in forever. Yeah, I had, let's see here, some cheesy eggs, delicious as well. Yeah, okay, so here's what happens, right? Your food has energy in it, right? When you eat it, your body is able to change that energy and make it into a usable form called glucose, and your body can then use that glucose in order to move. And motion is another type of energy, kinetic energy. Okay, so energy can absolutely change. We have a bunch of examples down here, right? Electricity can turn into light. It can turn into motion. Radiant energy from the sun can turn into plants, can help plants grow, right? Yeah, glucose, exactly. Glucose is the sugar that your body uses as energy. Okay, so energy can change, but the thing is, the total amount of energy in our entire universe cannot be created, cannot be deleted, and you can't add more. The total amount in the universe will always stay the exact same. Smiley faces, if that makes sense. We've talked about this several times, right? So if you were to mathematically add up all the energy in the world, it's always going to stay the same, even though within that calculation, it might be moving from one spot to another spot. Okay, so you can see a great diagram of this right here. The energy before will always equal the same amount of energy after, even if it looks a little bit different. Even if it looks a little bit different. Okay? So, how many of you like roller coasters? Go ahead, give me a green check if you enjoy roller coasters. Give me a red X if you do not. Let's see where most of our class stands. Awesome. Do you like roller coasters? Green checks. Do you not? Give me a red X. I am definitely a big green check. I love roller coasters. You've never been on one, Amanda, so you don't even know if you like them. I know, roller coasters, I just think they're so much fun. You get that little bit of an adrenaline boost. They're a little bit scary, right? And I am actually like, I don't super enjoy heights. Like, I'm not about to stand at the top of a skyscraper and look over the edge. Like, that, I don't enjoy that. But if I'm moving, it seems a little bit less terrifying, right? Awesome. Yeah, if you've ever been to any of the theme parks around California, I'm sure there's a lot of them that are super awesome. Yeah, okay. So I'm going to go ahead and show you a quick video. Go ahead and give me a green check when you finish watching it. It's all about how we see conservation of energy in roller coasters. Okay, smiley faces if you understand what we're doing. You're going to go ahead and see how is energy conserved or saved within a roller coaster. Let's go ahead and watch this. Give me a green check. Oops. Green check when you finish watching it. Here we go.
Welcome to the Physics Coaster, one of the world's most breathtaking rides in which you can unravel the mysteries behind roller coasters and learn about the math and physics put into this amusement park ride. For your safety, keep your hands, arms, feet, and legs inside the car at all times. Please sit in an upright position. Fasten your seatbelts and hold on tight to the handlebars, because this ride is going to blow your mind. As you can see, the roller coaster is climbing up the hill with the help of a chain lift. Now from here on, it is in the hands of gravity to control the ride. When the car was released from the chain lift, the roller coaster blasted down the hill. By doing so, the roller coaster converted the potential energy it had into kinetic energy. As the car approaches the ground, it acquires more and more kinetic energy, therefore more and more velocity, which explains the increased speed near the bottom of the track. The roller coaster is in the system, the total energy, otherwise known as the mechanical energy, remains constant. Mechanical energy is the sum of the potential and kinetic energy in a system. The roller coaster follows the law of conservation of energy. Energy cannot be created or destroyed. However, it can be changed from one form to another. In a roller coaster, the energy is constantly transferred between potential and kinetic energy when in motion. But eventually, due to friction from wind, track, and brakes, the energy is transferred to other forms such as heat and comes to a stop. So blame friction for stopping your thrill and enjoyment on roller coaster ride. Thank you for riding the Physics Coaster. You can now lift up the safety bar and exit to your right.
Green checks if you finished. Perfect. All right, everyone. So what I want you to go ahead and take a look at is I'm going to go ahead and share this with you. Right here. Okay, so take a look at this. So again, we're talking all about this idea of conservation of energy. So what we can see here is that at times, right, there was a lot of potential energy and very little kinetic energy. At other times, though, there was a lot of kinetic energy and very little potential energy. But in total, does it make sense how that still totals out to the same amount, right? So if we have 100% potential energy and 0% kinetic energy, that's still going to be the same as the total amount when we have 0% potential energy and 100% kinetic energy. Smiley faces, everyone, if that's starting to make sense. So in total, when you add it all up at each different point of the roller coaster, in total, it's still going to equal the total 100%. Okay. Now there is a really important exception because this is not an ideal situation. In real life, right, will a roller coaster keep on moving forever? If there was nothing else helping the roller coaster in real life, would it keep moving forever? Think about your own car. Once you step on the gas once, does it keep moving forever? No, because what's preventing it from moving forever? What is preventing it from moving forever? Yeah, there's brakes, right? There's wind or air resistance. What else is happening between the track and the actual car? Yeah, there's friction, exactly. So all three of those things are actually resulting in this slowing down even more. But remember, those are actually types of energy as well, right? Friction causes heat energy to be lost. So in total, if you were to add back in all of the heat energy that you're also losing, it would still equal 100%. Okay, so even in non-ideal situations, in total, it actually still does add up to the same amount. Okay? Awesome. The second law of thermodynamics is entropy. Now, entropy means the amount of disorder in a system. So think about this. In general, throughout your entire life, things have a tendency to get more and more disordered. Just think about your own room. How many of you have a room that looks like this or at some point has looked like this? Yes, exactly, Ireland, because of that friction that you're working against. Yeah. My room definitely does not look like this now. But I remember when I was in college and it was a small room with me and my roommate, who was also an even more disorganized person than me. This was definitely what at least her side of the room looked like at some points. Now, the reason for that is because it takes a lot of energy to put things back in an ordered manner. So just naturally, whether you're talking about human instinct or whether you're talking about the natural world, naturally things have a tendency to get more disordered. Okay, smiley face if that makes sense. I know, this is very messy. All right. Now, the reason for this is when energy changes, right? Because we've talked all about how energy can change, right? Just not be deleted or created. When energy changes, some of that energy becomes unusable. It becomes a form that we can't use very easily. And it's often lost as heat. Lost. Again, it's not being deleted. It's just becoming an unusable form. So you can see that over here, right? The total before and after, is the total still balanced before and after? Take a look at our diagram up here. Is the left side still balanced with the right side? Is the total still the same before and after? Think back to our first law, the conservation of energy. Is the left side and the right side still balanced and still equal? Go ahead, tell me in the chat box. Are we still balanced here? Yeah, of course, right? There's no like leaning here. So in total, we haven't deleted energy. We haven't created any new energy. It's still equal. But can you guys see here this gray part? This gray part is now unusable energy. So the problem is that even though we still have the same amount in the universe, as time goes on, the amount of usable energy becomes less and less throughout the universe. Okay, thumbs up if that's beginning to make sense. Now, there's still a lot of energy, right? So you don't need to worry about like someday in your lifetime there will be no energy left in the universe. But keep in mind that there's unusable energy that gets kind of lost in the universe. Cool. So what this means is that as useful or potential energy goes down when there's a change, that means entropy or disorder is increasing. This is why water flows downwards. This is why everything dies. It's why your batteries in your phone don't spontaneously recharge, right? That's why you have to go find a plug because your batteries don't just magically start getting full again. And that's why things cool off from hot to cold. Okay, so things have a tendency to become more disordered. Okay? So here's the thing though. Obviously not everything in the universe is always disordered, right? At some point you can clean your room, right? Smiley faces if that makes sense. At some point you can clean your room, become a little bit more ordered, right? Okay, so what this means is that smaller systems can become more ordered as larger systems become more disordered, right? So think about this in terms of the sun, okay? The sun has a ton of energy. It has a very high amount of energy, okay? But eventually, will the sun die? Think about what we just talked about on the last slide. Eventually, is the sun going to die? Tell me in the chat box. Will it eventually run out? Yeah, it's not going to be the same sun that we have now. As time goes on, it's going to lose that energy. Okay, so the sun's energy flows from very, very high to very, very low. Smiley faces if that makes sense. So obviously that's not happening in our lifetime, but at some point the energy is being lost. Okay, energy, you can see that in green here. The sun goes from very high to low. However, as that's happening, trees can actually take advantage of that, right? Trees can take advantage of the fact that the sun's energy is going from high to low, because that energy that gets released, the trees can then take that energy and they can do what? What do trees do when they get energy from the sun? They begin to grow, exactly. So trees can take advantage of the sun losing energy in order to begin growing. But let's think about this. Is a tree ever going to create more energy than the sun is losing? Tell me in the chat box. Is a tree ever going to be able to create more energy than the sun loses? No, okay, so not only is the sun losing some energy that's becoming heat, some of that energy going into the tree, it's not going to ever make more than what the sun lost in the first place. So take a look over here, right? If the sun is losing a lot of energy and the tree is only using that to become a little bit more ordered, in total, okay, do you think in total are we becoming more ordered or more disordered? Tell me in the chat box. In total, what do you think is happening? If the sun is a really big negative and the tree is a small positive, in total, do we end up more negative or more positive? Tell me in the chat box. So we've got a big negative. Let's say this is like negative 100 and the tree is like positive 20. In total, what does that mean? Do we end up more disordered, negative, or more ordered, positive? Yeah, exactly. So in total, right, the tree is never going to be able to make up for what the sun loses. So in total, the system itself does become more disordered. Smiley faces if that's beginning to make sense, okay? So even though the tree can take advantage of it to become a little bit more ordered, over the entire universe in total, we are becoming more disordered. Awesome. This is number 1 in your ticket. It's also going to be related to number 3 in your quiz when we do that a little bit later. Go ahead, take 30 seconds to answer this. So you should be choosing the option that says high, comma, disordered. That's how we fill in these blanks correctly. Green checks. Go, go, go. Need a few more green checks. Alyssa, Amir, Andrea, Brianna, Chanel, Damien, Dusty, Dorian, Dylan, Edwin, Elias, Jasmine, Josiah, Jody, Letty, Blossom, Tristan, Whitney, Yolese. Green checks for number 1. And again, this will also be related to number 3 in your quiz later on. All the attendance tickets are always related to our quizzes. Perfect. Okay, guys, so let's go ahead and actually take a look at how this idea of entropy, the sun kind of losing this energy, is able to actually power a lot of other things in the earth. Okay, so let me go ahead and grab this video. What tab do I want to be in here? Oops, sorry, something's in the chat. No, so remember, Efren, that there is actually heat being lost into the rest of the solar system. Like all the heat that the sun releases, all the radiant energy that the sun releases doesn't get to Earth, right? Think about the fact that the sun is very big, but the solar system is even bigger, and the Earth is a very small part of that solar system. Yeah, good question. I know, that's why it's a little bit hard to think of, right? Because we have a very limited perspective compared to how big, right, our solar system actually is. All right, let me go ahead and share this video with you. Green checks when you finish watching it. Go, go, go.
The Earth receives about 90 petajoules of energy from the sun every second. That's a lot, enough to satisfy all human energy needs thousands of times over. However, the Earth also radiates an equal amount of energy back into space as heat, an almost equal amount anyway. The Earth is gradually heating up, but that's another story. So if energy in equals energy out, how can we possibly be using any energy to do anything? What matters, it turns out, isn't simply energy, it's useful energy. And energy is useful when it comes packaged in a low entropy form. The total amount of energy in any closed system can't change, of course. Energy is conserved. But that energy can be in different states of usefulness. There's useful energy in the water behind a dam, which will flow until the level is the same on both sides, but will never go back up. Or in hot tea, which will melt a cold ice cube until they reach a medium temperature. You never see tepid tea spontaneously generate an ice cube while heating up, even though the total energy would be the same. So useful energy is low entropy, out of equilibrium energy that can be put to work to turn a turbine or push a piston or melt an ice cube. Useless energy, meanwhile, can't be put to work. It's out there in the form of waste heat or noise or the potential energy of a ball just sitting on the ground. We can't really do anything with it. For example, gasoline and air carry useful low entropy energy. By burning them together, we can accelerate a car, drive for a while, then put on the brakes and stop. The total energy of the world remains constant during the trip, but useful chemical energy is converted into useless high entropy heat and noise. The energy is still there, but we can't reclaim it to power any more cars, as convenient as that would be. And thus it is with the Earth. The sun sends us energy in a convenient, useful, low entropy form, mainly as photons of visible light. This energy gets absorbed and used and degraded by various processes here on Earth until we radiate it away in a much higher entropy form. Lots of infrared photons. For every visible photon we receive, the Earth radiates about 20 infrared photons out into space. Even though there's a balance of energy in with energy out, the entropy of the energy has gone up 20 times.
All right, green checks if you finished watching that. All right, so thumbs up if that's starting to make it a little bit clearer, that the total energy, right, is still always the same amount, but again, at some point, a lot of that energy becomes useless, right? It's no longer useful, right? So they show this example of the car, which is a really great example, right? We need fuel for our cars, which is useful chemical energy. So this is useful chemical energy. But as we begin to drive our car, right, we generate heat, we generate noise, which becomes useless energy. So as time goes on, right, we have useless energy, more useless energy. And the amount of useful energy, this chemical energy, has gone down to where we can't use it anymore, right? So in total, it still equals the same amount, but in terms of what we can actually use, we're losing that, okay? That is entropy, this idea of becoming more disordered, losing useful energy. Give me a smiley face if you understand. Smiley face if you understand. Awesome. Looking good. All right, so that's our second law of thermodynamics. Our third one is about temperature now. So temperature, the third law of thermodynamics states that all motion stops at absolute zero, or that all motion would stop at absolute zero. We're going to talk about that in a few moments. So there are a couple different temperature scales that we're familiar with. Tell me in the chat box, what temperature scales do you already know? Okay, how do you measure temperature in the US, for example, versus how do we measure temperature in the UK? Go ahead, tell me in the chat box. What are the two different scales that we are very familiar with? Think about your own house. If I were to ask, what temperature is your house? How would you tell me what temperature your house is? You would give me a number and then a unit. What's that unit? Awesome, I see Noah typing. I see Arrow typing. Go ahead, everybody, we should know. Looking good. Make sure you're participating. Again, this helps to reinforce your own learning. Your own learning. Awesome. I got an answer from Ireland. Yes, what does do you guys know what the F stands for? I know it's a very difficult word to spell. Right, so Fahrenheit. I think I said that one correct, spelled it correctly. Yeah, it's a weird looking word. And then yes, C for Celsius, right? C for Celsius. So those are the two scales we're very familiar with already. However, there's another scale that scientists, chemists use more frequently, and this is called the Kelvin scale. All right, so 0 Kelvin, all right, is the lowest that the Kelvin scale can go, which is why they use the Kelvin scale, because 0 is the absolute lowest temperature. And this is the temperature where all motion would stop. It's called absolute zero, and in layman terms, in yours and my terms, that would be negative 460 degrees Fahrenheit. Very, very, very cold. Exactly. So what I'm saying, Ireland, is the Kelvin scale doesn't have negatives because scientists intentionally made the Kelvin scale so that 0 was the lowest temperature. Smiley faces, everyone, if that makes sense. Yeah, so that's why this one is 0, whereas Fahrenheit, right, you have to say negatives all the time, which gets inconvenient, right? Saying absolute 0 is cooler than saying absolute negative 460, right? So here's the thing, guys. Remember that all particles in our universe have some motion. Even the coldest things in our universe still have a tiny bit of motion. Remember, if you were to zoom in on them on an atomic level, they would just be vibrating back and forth, okay? But at no point does molecular motion completely stop in our universe, because it's just not possible. All right, so in our universe, it is not possible for us to reach absolute 0, and the reason why is because heat always moves from hot to cold. Okay, take a look up here. Heat will always move towards things that are colder, which means think about the ice in your freezer. In order for your ice to be frozen, does the freezer need to be hotter than the ice or colder than the ice? Tell me in the chat box. Does the freezer need to be hotter or colder than the ice you're trying to freeze? It needs to be colder, because that way the heat can be removed from the ice and leave the ice, all right? And that way your ice can freeze, okay? So that's the same thing that's true for anything, right? That if you want your food right here to freeze, you need to actually remove the heat. So again, things flow from hot, so your food is hotter, and your freezer is colder, right? So things flow from hot to cold. Okay, so you're removing heat from your food. However, in order for you to get to absolute 0, you would need a freezer that's colder than absolute 0, which is not possible. We can't have more than the lack of motion, right? Smiley faces if that makes sense. You would have to have a freezer that's even colder than absolute 0, which is what we're trying to get to in the first place, okay? So we've gotten really, really close to absolute 0, but we can't exactly get to absolute 0, at least not yet. We'll see what happens in 100 years, right? Cool. All right, go ahead, match these up on the whiteboard. I want to know, do we remember, here are the 3 laws we just learned, right? And here's their definitions. Go ahead and match those up. Use your whiteboard tools. Please use thin lines. Please use any color but red. Thin lines and any colors but red. Looking good. Get your answers up there. Sorry, 1 second, everyone. All right. All right, I'm going to go ahead and pause your tools up here. Looking good. All right, let's go ahead and shrink this down. And let's go ahead and see whether or not we got this correct. All right, everyone. So conservation of energy, this is an easy one. We all know this one. All right, so the conservation of energy, right? Energy cannot be created, it cannot be destroyed, it can only be changed, right? When we say the word conserve, we think of this idea of saving. Awesome. Now, entropy versus temperature, right? We just talked about this, okay? So think about this idea of absolute 0. Absolute 0, does this have anything to do with disorder, or does it have to do with temperature? Tell me in the chat box. Absolute 0, is that something to do with disorder or something to do with temperature? Go ahead, tell me in the chat box. Yeah, remember, absolute 0 is a temperature. It's the temperature at which all motion stops, right? So absolute 0, we could also call it 0 K, 0 Kelvin. Okay, so if that's being said, do you think that's the law related to entropy or the law related to temperature? Go ahead, tell me in the chat box. Which law is this related to, entropy or temperature? Yes, this would be the law related to temperature. So all motion stops at absolute 0 is actually the third law that relates to temperature. Smiley faces if that makes sense. All right, it's the third law that relates to temperature. Awesome. All right, the last one here, entropy, usable energy decreases and disorder increases over time. Remember, anytime you think of the word entropy, you should think of this idea of disorder. So we got these two a little bit backwards. That's okay though. We're fixing our mistakes now, and that should help to reinforce our own learning. So let's go ahead and answer number 2 in your ticket. You have 30 seconds. It's also going to be related to 1 and 2 in your quiz. Green checks when you have number 2 in your ticket saved. Yes, of course, Ireland. Go, go, go. 20 seconds, everyone. All right, waiting on a green check from Amir, Andrea, Bree, Chanel, Damien, Dusty, Dylan, Edwin, Elias, Jacob, Jade, Jasmine, Josiah, Letty, Miguel, Oscar, Blossom, Rozzy, Tristan. Okay, yep, Miss Hale, I can go ahead and hold on for a moment. Okay, I know Ireland's using the restroom right now, but Ireland did ask a good question earlier that said, why not cold to hot? So if you were with me last quarter, we learned that cold is actually the absence of heat. Cold is not a real concept. Okay, so cold is actually just the absence of heat. So in order for heat to move, it needs to move from a place where you have heat to a place that's absent of heat. All right? So it moves from hot to cold. So from where there's heat to where there's no heat. Can't move the opposite way because there's no such thing as cold. Smiley faces, everyone, if that makes sense. And if Ireland comes back, we'll make sure that she hears that too. Cool. All right, everyone, looking good. All right, so the last thing that we need to talk about, everyone, is just a couple things about heat energy. So remember that when we have phases of matter, the actual particles themselves are not changing their identity, right? The chemical identity stays the same because phases are really just physical changes. Oh, sorry, Ireland. So I was telling everyone based on what you asked earlier. So you can't have heat travel from cold to hot because cold is not a real thing. Cold is actually just the absence of heat. So heat can't travel from where there's no heat to where there is heat. So it'd have to go the other way, from hot to the absence of heat, hot to cold. Yeah. All right, so actual particles don't change. Instead, all that changes is how they interact, right? So solids, the H2O molecules will vibrate. Liquids, the H2O molecules can kind of move around. Gases, the H2O molecules can move so fast they can escape. But no matter what, they are always still H2O molecules, right? We've talked about that a bunch of times. Okay, so let me go ahead. I'm going to go ahead and share this with you. Let's take a look at this. All right, everyone, thumbs up if you can see my screen up here. Give it a moment to load. All right, guys, so take a look over here, right? So currently, what state of matter is this? Tell me in the chat box, what state of matter do you think this is? Actually, I'm going to change it to water. What state of matter do you think this currently is? Tell me in the chat box. Think about, remember, solids kind of keep their shape, liquids will flow, gases will spread out. Yeah, this is solid. So this right now is actually ice, okay? So it's keeping its shape, right? It's not flowing, it's actually kind of keeping its shape. But take a look at those molecules. Are the molecules still moving a little bit, right? Remember, is it possible to get to the point where there's no motion? Yeah, those molecules are still moving. We cannot get to absolute zero, right? Can't get to absolute zero, right? We could get really, really cold and they could slow down. But in reality, right? As cold as we get, they're still slightly moving. No, this is solid. This is solid. It's even though the molecules are moving, as long as all the molecules together are keeping their shape, that's a solid. Cool. All right, so let's take a look at a liquid. We can heat this back up. And now we can see they begin to actually be able to flow past each other, right? So this is a liquid where they begin to actually flow around, move past each other, right? They're getting a little bit more energy. There we go, getting a little bit more energy. Good. Yep, beginning to melt. And then what happens as I continue to add energy? Take a look at the actual individual molecules. What's happening to their motion? It's a little bit hard to see, I know, with the lag, but take a look at the motion of some of them. Some of these molecules are going super, super crazy. What are they doing? Yeah, it looks like popcorn. So we're getting to gaseous stage. And take a look at a lot of these little molecules are spinning super, super fast. So they're increasing their motion from that added heat energy, that added thermal energy. Smiley faces if that helps you better understand this idea of heat here, of how thermal energy affects phases. Yeah. All right, good. So there are two things that we need to know. The first is the heat of fusion. So the heat of fusion is the amount of energy you would need to add to turn a gram of a solid into a liquid. Okay, so in order to melt it. So when you think of fusion, you should think of melting. Fusion means melting. All right, now the heat of vaporization would be the amount of energy you need to add to turn a gram of liquid into a gas. All right, so vaporization, you think vapor. Vapor means gas, right? So vapor means gas. Smiley faces if that makes sense. Heat of vaporization, the amount of heat you need to add to turn it from a liquid to gas. Okay, it's also the amount that you would need to remove to go the reverse direction. Same with heat of fusion. If you remove the heat of fusion, you go reverse. You go from liquid to solid. If you remove vaporization, you go from gas back into a liquid. Okay, so those are just some quick definitions that you need to know for your quiz. Okay. Now, I do want to remind you guys that you should have seen this yesterday in your lab. What I want you to notice is your lab, did it steadily increase in temperature? Tell me in the chat box, did we actually get a steady increase in temperature? Was our graph a straight line? Was our graph a straight line from yesterday? Tell me in the chat box. Quickly, guys, we only have 2 minutes left. No, it wasn't. All right, so your hypothesis yesterday should have been disproved. We actually disproved our hypothesis because it was not a straight line. It was a curve, right? Which means that it was not steady. Okay, smiley faces if that makes sense. Our increase in temperature was not steady. Okay, this is a very surprising thing that a lot of students see, is that there are points where the temperature actually stays the same. And those points are whenever the phase changes are occurring. So whenever we have two phases together, like a solid and a liquid during melting, or a liquid and a gas during boiling, the thermal energy does not increase the temperature because all it's being used is to separate the molecules, to take those solid molecules and begin to pull them apart. Smiley faces if that makes sense. During a phase change, you're only separating, not increasing the temperature. Yes. Once you have a single phase though, once it's just a solid or just a liquid or just a gas, then that thermal energy can actually be used to start increasing the speed of the molecules, which does increase the temperature, which is why here we can see increases, but at phase changes we cannot. All right, so let's go ahead and match those up. So we've talked about thermal energy, right? Phase change, single phase, heat of fusion, heat of vaporization. Go ahead and match those up on the whiteboard, and then we'll be finishing up, and I will give you your last word. All right, go ahead quickly, work on the board. I know we're going a little bit over here. Letty, it'll be in the recording. That'll be uploaded at 2 o'clock, but I have another class to go to, so I won't be able to go back to it right now. Awesome, awesome, awesome. All right, guys, I'm going to go ahead and pause these. I do see a pattern emerging, though, so that's good. Let's go ahead and match these up. Looking good. So thermal energy, yep, thermal energy is a measure of the motion of a substance's molecule. Phase changes means that this is the time when thermal energy just separates the molecules, but the temperature does not increase. There is not a steady increase in temperature when there's a phase change. During a single phase, then the thermal energy can increase the speed, which does increase temperature. Heat of fusion is how we change a solid into a liquid. And then last but not least, the heat of vaporization is how we change a liquid into a gas. All right, so this is going to be number 3 in your ticket. It will be related to 4, 5, and 6. Give me a green check when you have that saved. All right, I'll go ahead and give that to you right now. And then I'm going to go ahead and just tell you in the chat box, the last word for today is fuse. Okay, so last word for today equals fuse for number 4 in your ticket. All right, so once you've got all of that, I will see you all later. Thanks so much, everyone. Have a wonderful day. Again, that last word for today, everyone, is fuse, just because I want to give everyone as much time on here as possible. All right, once you're done, though, please log out. I do have another class to go to. No worries, Efren. I'm going to leave it on the board. So again, I'll just type up here, maybe, that the last word for today equals fuse. Okay, thanks so much, everyone. And sorry, that's question number 4 in your ticket. So attendance ticket number 4, the last word equals fuse. Cool. Bye, everyone. Go ahead and log off. I do have another class to go to. Bye.